Welcome to today's presentation entitled Introduction to Digital Signal Processing. My name is Dr. Jim Batty, and I work at the NASA Langley Research Center in Hampton, Virginia. I am a member of the NASA Engineering and Safety Center Flight Mechanics Technical Discipline Team. This presentation is part one of a four-part discussion about digital signal processing and is sponsored by the NESC as part of its educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations and a number of technical disciplines of interest to the NASA community. Today's presentation is entitled Mathematical Concepts, and we will discuss the mathematical basis of digital signal processing and introduce the framework for the discussions to be continued in parts 2 through part 4. An overview of the four-part series in digital signal processing is presented here. Part 1, today's discussion, will talk about the mathematical definitions and prerequisites and application techniques that one would use for digital signal processing. We'll discuss Fourier transforms, both continuous and discrete Fourier transforms, and convolution, and define what that means a little bit later. We'll discuss discrete Fourier transforms and fast Fourier transform algorithms, or FFT algorithms. We'll also conclude today's discussion with the Shannon Sampling Theorem and the data aliasing, as it's called, which is related to improperly sampling a signal, or sampling a signal at a rate that's too slow to capture the spectral characteristics of that data that you're sampling. In part 2 of this presentation, which is entitled Power Spectral Density Basics, we'll discuss the techniques used to estimate the spectral characteristics of waveforms, which is one of the more important applications of digital signal processing, where we can evaluate a given time domain signal and interrogate what sort of frequency content it has. We will also include in part 2 a power spectral density demonstration, where we'll take a signal with known inputs or known content, and we'll show how PSD can be used to identify those characteristics. Part 3 of this four-part series is entitled Implementing Discrete Filters. And in this presentation, we'll discuss how one would convert from a continuous or Laplace domain filter to discrete or Z-domain filters. And that's generally referred to as Tustin's rule or the bilinear transformation. And one can readily convert a filter from the S-plane or Laplace domain form to the Z or discrete domain fairly readily. And then also, with that, we'll show how you can implement recursive filters to do the discrete filters, which are a little bit simpler than continuous domain filters that require integration of parameters. And finally, in part 4 of this four-part series, which is entitled Typical GNC Applications, I'll show how you actually can use discrete filters to do various things. You can verify transfer function magnitudes of discrete filters. So if you're given the coefficients of a discrete filter, you can compute its magnitude and phase and verify that you have what you think you have. And then I'll also show how you can use a discrete filter to implement filtering of some signal. And in this particular example that I'll show in part 4, we'll show how to implement a notch low-pass filter and use it to filter out higher frequency content of a signal. We'll start today's presentation with a definition of the Fourier transform. For a continuous function of time f of t, the Fourier transform, which is referred to in this presentation as capital F of omega, and its inverse, or the synthesis equation, are both defined as shown in the first equation here. The equation on the left is computing the Fourier transform of the time domain signal, and that results in a function of frequency. The equation on the right, generally referred to as the synthesis equation, converts back from the frequency domain to the time domain. There's an alternate form that can be used, that some folks use, that we will discuss in the presentation as well also today, is shown as the second form, and it's very similar. You have the same analysis equation on the left, which converts from the time domain to the frequency domain, and the synthesis equation on the right, which converts back from the frequency domain to the time domain. Yet the difference between the two forms shown at the top and the center of the slide is the first equation has a scaling of 2 pi applied equally to the analysis portion and the synthesis portion as the 1 over the square root of 2 pi multiplied by each integral. In the second form, that factor 2 pi is applied solely to the synthesis equation. And they are equivalent. They will do the same functions as far as computing Fourier transforms and reconstructing the original time domain signal from the Fourier transform. So it should be you should be clear which form you're using if you're working with Fourier transforms. And also pay particular attention to the second form shown before, the synthesis equation, which converts from the frequency domain back to the time domain. And as I said, you'll see that it contains a factor of 1 over 2 pi, which is basically a scaling for the converting from the frequency domain back to the time domain. It will also affect the discrete Fourier transform that we'll present in a few slides from now. And that discrete Fourier transform will include a scaling factor that's used to apply to the frequency domain signals if you want to go back and reconstruct the time domain signal. So the form that we'll be using in today's discussion and the other 3 parts of this 4-part series is the second form shown in the center of this slide. As an example of what you would get from a Fourier transform, let's assume we have a simple function of time that's nothing more than just a cosine of at, where a is the frequency in radians per second of the signal on a unit amplitude cosine wave. Then the Fourier transform f of t, as defined in the previous slide, would be f of omega is 1 over the square root of 2 pi times the integral from minus infinity to infinity of f of t, which is, in this case, cosine at, times e to the minus j omega t integrated over dt. Then one can show from mathematics that results in a expression to the right of the equation, which is square root of pi over 2 times delta of omega plus a plus delta of omega minus a, where in this case delta is the direct delta function, which is defined such that delta of x is 0 for all x except at x equals 0. And at x equals 0, it has a value sufficiently large such that the integral from minus infinity to infinity has a value of 1. So, given that definition of the delta direct function, the Fourier transform f of omega of cosine at then would look like the waveform that's shown plotted at the lower portion of this slide. And what you'll see is the little symbols, the x data points, indicates that the Fourier transform is 0 everywhere except at omega equal minus a and omega equal plus a. So therefore, the Fourier transform of a simple single sinusoid f of t equals cosine at would produce single spikes in the output data at plus or minus a. And so that makes Fourier transforms very useful for identifying and extracting frequency content of signals. So for instance, in general in the real world, f of t would be some waveform whose content is unknown. And by computing a Fourier transform, you can then extract out the Fourier transform that would show little spikes every place where you have a particular periodic or sinusoidal frequency content. There are some properties of Fourier transforms that will be very useful in performing some of the analysis techniques that we'll discuss in this 4-part series. And the first of these is the linearity property of Fourier transforms. Now, if f of t is composed of many sinusoids, not just one as in the simple example that I just showed on the previous slide, the linearity property of Fourier transform requires that the Fourier transform of f of t will have discrete non-zero spikes or non-zero values at each distinct frequency of those individual sinusoids. And that's an essential property of Fourier analysis that's the key to the real power that you can derive from it. For example, if the f of the symbol I show here is like f with curly brackets, if that represents the Fourier transform as described earlier in this presentation, then the linearity property would say that the Fourier transform of the sum of some function a times f of t plus some function b times g of t is the same as a times the Fourier transform of f plus b times the Fourier transform of g. The convolution property, which we'll define what convolution means on the next slide, the convolution property of Fourier transforms, where in this case an asterisk would define convolution and a dot would denote ordinary multiplication, the Fourier transformation of the convolution of f of g and g of t would be proportional to the product of the Fourier transforms of f and g. The multiplication property of Fourier transforms says the Fourier transform of the product of f of t and g and t is proportional to the Fourier transform of f convolved with the Fourier transform of g. That is, said another way, multiplication in the time domain is the same as convolution in the frequency domain, and vice versa. That also will be very key part of digital signal processing that will unlock a lot of its power, as we will see in this 4-part series. As described on the previous slide, we referred to convolution, and so what is actually the definition of convolution? It's a mathematical operator acting on two functions which computes the integral of the product of the two functions, where one is reversed and shifted in its independent variable. And most of the time that independent variable would be time for the applications that we'd be interested in here. So mathematically put, the first equation shown defines convolution. And it says the time signal, that's the convolution of f of t and g of t, is nothing more than integral from a to b of f of tau, g of t minus tau, d tau, where tau is just a variable of integration, and the domain tau equals a to b just depends on the domain over which the functions f and g are defined. And again, herein and most of this presentation, an asterisk will be used to denote convolution as opposed to normal multiplication. You can also compute the discrete convolution of sequences of n samples of functions f and g, as shown at the equation at the bottom of this slide, which is very similar in appearance to the continuous or time domain or continuous implementation of convolution at the top. And that just says the discrete samples of the convolution of f and g, which consists of n samples, where m, the index of those n samples, goes from 0 to n minus 1. What are the uses of convolution? Well, typically in signal processing applications, as we'll describe in this series, one of the functions that would be used in the convolution is a filter's impulse response, which also is known quite often as the filter kernel. The other function in the convolution would be some signal to be processed or conditioned by the filter. So for instance, if you had a low-pass filter that you wanted to use to remove noise, high-frequency noise from some signal, one of the signals, call it f of t in the previous example, would be the impulse response of a low-pass filter. The other signal would be x of t, where x is some waveform that you wanted to filter. Then if you computed the convolution of the filter kernel times the signal to be processed, you would in effect process that signal through that low-pass filter, thereby removing the higher frequency content. Another use of convolution that's not directly related to signal processing, but is very useful also, it can be used to multiply term by term two polynomials. So let's say, for example, you had two polynomials in x, p sub x and q sub x, defined as just polynomials. So p sub x is p0 plus p1x plus p2x squared plus dot 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 plus p sub n, x to n, x to the nth power. And similarly for q. If you just wanted to compute the term-by-term multiplication of p sub x times q sub x, you could write it out manually and collect all the terms of powers of x, and then you would result in the equation shown for r of x there. Another way to do this with convolution is you define arrays of the coefficients of the polynomial p and the coefficients of the polynomial q, and compute r as the convolution function that you might find in MATLAB or Octave or other analysis packages. You could then compute r as the conv of p comma q. And then it would actually return back to you the coefficients of that multiplication of p of x times q of x. Okay, what are the properties of convolution? There are several properties that we'll discuss here. The first is the convolution is commutative. In other words, the convolution of f of t and g and t is the same as the convolution of g and t and f of t. And you can see that from the basic definition of convolution. If you just substituted f and g in the equation shown earlier, or g and f in the equation, you get the same answer back. It's also associative. If you take the convolution of three functions, then the f of t convolved with the convolution of g and h would be the same as the convolution of f and g convolved with h. It's also distributive. If you have the f of t convolved with g of t plus h of t, that's the same as the convolution of f and g plus the convolution of f and h. As we discussed earlier, it has a linearity property that some constant k times the convolution of f and g is the same as k times f of t convolved with g of t, and that's the same as f of t convolved with k times g of t. And finally, the convolution theorem that we discussed earlier too, that replaces convolution in the time domain with multiplication in the frequency domain. So the Fourier transform of the convolution of f of t and g of t is the same as the product of the Fourier transform of f of t times the Fourier transform of g of t. And as also mentioned earlier, this last one is very important for digital signal processing. It states that the inverse Fourier transform of the product of the Fourier transform of f and the Fourier transform of g is proportional to the convolution of f and g. That is, convolution operation can be replaced with two Fourier transforms, and multiplication of these term by term, and then an inverse Fourier transform. And you might wonder, well, why would that be useful? We'll discuss that in a couple of slides from now, that can be used to very efficiently compute the convolution of two very large sequences of data. Okay, how do we compute the convolution? As we showed earlier, what I will refer to in this presentation is just brute force. Do it exactly as shown from the summation that was previously presented a few slides ago. And again, to refresh your memory from that, what that says is the n samples of the convolution of f and g has indices 0 to n minus 1. It's just a summation from 0 to n minus 1 of f of n times g of m minus n. And you'll note that's quite a few calculations involved there, because for every value of m from 1 through n minus 1, you have to do a summation of those entire sequences over the indices n equals 0 to n minus 1. So basically you're doing n squared calculations there. And many digital signal processing applications require very large sequences of numbers to be processed. Usually they're like 1024, 2048, 4096 points, etc. And so therefore, since that calculation above is proportional to n squared, if n is a large number, n squared is a lot of calculations, and it can take an extremely large time to compute. Also, one thing to point out that will be instrumental in the discussion today too is notice the n's that I gave as examples there: 1024, 2048, 4096. Why those specific numbers? Those happen to represent the powers of 2. And it's very important in the signal processing that the n, the number of samples of a signal that you sample to perform the Fourier transforms, that for discrete Fourier transform should be a power of 2. So 64, 32, 64, 128, 256, 512 samples, etc. And then also, as I described, just performing this so-called brute force summation can be very inefficient for very large sequences. As a result of that, there's been more numerically efficient algorithms that were developed, one of which is called the fast Fourier transform, or FFT. And it's been shown that it can increase the time required to perform convolution of the order of n times log of n, where n is the number of samples in the sequence. So if you have a large number like 4096 points, then it can increase the amount of time, or I guess decrease the amount of time required to perform that by 4096 times the natural log of 4096. So it's a huge savings in efficiency compared to just doing the summation as shown above. But a key point to point out is FFT is an algorithm or technique for performing convolution. It's not really a different mathematical concept. Sometimes people confuse that. They wonder, how is an FFT different from a DFT, or discrete Fourier transform? It turns out it's no different at all. It's just a more efficient algorithm for computing discrete Fourier transforms. And as we'll discuss in part 2 of this discussion, which is entitled Power Spectral Density Basics, we'll also touch on PSDs or power spectral densities. How are they different from FFTs? And again, they're not different. PSD is just is a technique that includes some additional techniques for refining or conditioning the data that you're going to analyze to make it a little bit more manageable. But again, FFT is not a different technique, not a different concept, it's just a different technique of computing discrete Fourier transforms. And you can also show, as we discussed earlier, you can compute the convolution as the inverse DFT of the discrete Fourier transforms of the two signals being convolved. That also is very efficient to do. So what is the real discrete Fourier transform? If we have discrete samples of values of some periodic function f of t sampled at regular intervals, it will produce a sequence of time samples, f sub n, where n goes from 1 through n, lowercase n, the index goes from 1 to uppercase n, where uppercase n is the number of samples. Or conversely, sometimes and quite often you will see those indices are renumbered 0 to n capital N minus 1 instead of 1 to capital N. But they're still result in a collection of n samples of the signal. And as described earlier, if you note the footnote at the bottom of this slide, the function f of t has kind of two restrictions for performing discrete Fourier transforms. It must be periodic with a period of n samples, and n must be some power of 2. The periodicity requirement just says basically that f of t is the same as f of t plus k times n for any integer k. Now that on the surface might seem to be a limitation because quite often the waveforms we look at can't be guaranteed to be periodic. Well, you can just basically make the assumption that they are if you have a sample of n or a collection of n samples of some waveform. That can be thought of as just, if the samples are large enough, it's just a periodic sequence that will repeat that pattern. And so you still can analyze the content of the signal without knowing for sure that it's truly a periodic signal, such as a collection of sine or cosine waves. Going back to the second bullet here then, the real discrete Fourier transform, or DFT, would produce n over 2 plus 1 coefficients, x sub k, where k varies from 0 to n over 2. And again, since n is the power of 2, n over 2 is an integer value, so then k has integer values from 0 to n over 2. The real DFT, x of k, and its inverse, x of n, are defined as shown in the equation at the center of this slide. And this basically has been presented before. This is just the analysis equation on the left, which produces the discrete Fourier transform coefficients x of k, and the so-called synthesis equation over on the right, which takes those discrete Fourier transform coefficients and reconstructs the time domain signal. And you see they're just a product. The discrete Fourier transform coefficients on the left, x of k, is just a summation from lowercase n equals 0 to n minus 1 of the values of the sequence, the sample values x of n, times e to the minus j 2 pi over n times k n. And the DFT of a discrete sequence from a periodic function is the discrete domain equivalent of the continuous Fourier transform of continuous signals. And again, as we pointed out earlier in the presentation, note the factor of 1 over n on the synthesis equation. That's the equation on the right that converts from the frequency, the DFT coefficients, capital X of n, back to the time domain sequence values x of n. That 1 over n factor is equivalent to the 1 over 2 pi in the synthesis equation of the second form shown for the continuous Fourier transform. It's basically the same scaling. 1 over n would be the total domain, or total period of the discrete Fourier transform coefficients, where 1 over 2 pi is the period of the time domain sequence. Now we'll present the real and imaginary forms of the discrete Fourier transform. You may recall from Euler's identity that e to the minus j theta can be expressed as cosine theta minus j times sine theta. So therefore, the coefficients of the discrete Fourier transform x sub k that were presented on the previous slide can be, and usually are, separated into their real and complex parts, which we will denote here as real re in curly brackets of x sub k and im in curly brackets of x sub k. Or alternately, as we'll see on the next slide, they can be written in polar and polar form, which consists of the magnitude and phase. So breaking the discrete Fourier transform equation on the previous slide into its real and imaginary parts, or separating it into its real and imaginary parts, you get the first equation shown below, which is the so-called analysis equation, where you're computing the discrete Fourier coefficients from the original time sequence x sub m. The real discrete Fourier transform coefficients x sub k is equal to the summation of m equals 0 to n minus 1 of x sub m times cosine the basis frequencies 2 pi k over n times m, where the index k runs from 0 through n over 2. That is, they're n over 2 plus 1 real discrete Fourier transform coefficients. The imaginary coefficients are equal to the negative of the summation from m equals 0 to n minus 1 of x sub m, this time times the sine of the basis frequencies 2 pi k over n times m. And again, k index runs from 0 through n over 2. The reverse transformation, also called the real inverse discrete Fourier transform, is also referred to as the synthesis equation, is shown as the second equation on this slide. And that would be used if you wanted to reconstruct the original time sequence x sub m from those discrete Fourier transform coefficients in their real and imaginary forms. One thing to note in this equation, though, is you'll notice we've made a change in notation here. The real part in the synthesis equation that's used to reconstruct the sequence x sub m is denoted as re with the x sub k with a bar over it, and the imaginary part to the right of the equation is the im and with x sub k with a bar over it. The barred x sub n parameters are the scaled DFT coefficients as defined at the bottom of this slide. So the re of x sub k with a bar over it is nothing more than 2 divided by n times the re of x sub k that you would get from the equation at the top of this slide. If k is equal to 0, not equal to 0, or not equal to n over 2, that is, not at the ends of that sequence of coefficients, where k, recall, runs from 0, 1, 2, all the way up to n over 2. If it's at 0 or n over 2, the scaling applied is 2 over n. If you're at the endpoints, k equals 0 or k equals n over 2, the scaling of the real discrete Fourier transform coefficient is 1 over n. Likewise, the scaling for the imaginary coefficients, which is denoted as im of x sub k with a bar over it, is minus 2 over n times the imaginary part im x sub k, again computed from the equation at the top of the slide towards the right. And that's again for all k's from 0 through n over 2. But however, note the imaginary part at the endpoints, that is k equals 0 and k over 2, is by definition always 0. So there will be no values for the imaginary im of x sub k computed from the equation at the top. They will always be identically 0. These scale DFT coefficients in the synthesis equations apply that 1 over n scaling that we saw in the equation on the previous slide before we separated it into its real and imaginary parts. And also that is equivalent to the 1 over 2 pi factor that we saw earlier in this presentation for the continuous form of the Fourier transform. And that's that scaling factor is a very common source of error or mistake that people might make when they compute the discrete Fourier transform coefficients using the top equation. If they forget to apply that scaling, then when you try to reconstruct, or if you try to reconstruct the original sequence x sub m in this case, you won't get the right values, not having applied that scaling. Now on the next slide here we'll talk to the discrete Fourier transform in its magnitude and phase form, which I mentioned on the previous slide can be equivalently written instead of the real and imaginary parts. And in so doing, the equations on this slide can be used to transform back and forth between the real and imaginary parts, again, which were denoted by RE in curly brackets of x sub k and IM in curly brackets of x sub k, to the magnitude and phase form, or M of x sub k and phi of x sub k. So the first set of equations here is if you have the real and imaginary parts and you want to compute the magnitude and phase. The magnitude is just simply the square root of the sum of the squares of the real part and the imaginary parts. The phase is the arctangent of the imaginary part divided by the real part. And once again, the indices k run from 0 through n over 2. That is n over 2 plus 1 total discrete Fourier transform coefficients. Or if you have the magnitude and phase and you want to convert it to the real and imaginary part, the second set of equations would apply. The real part of the discrete Fourier transform coefficient is the magnitude times the cosine of the phase angle. The imaginary part is equal to the magnitude times the sine of the phase angle. And again, recall at the ends of the sequences, that is k equals 0 and k equals n over 2, the imaginary parts are always identically 0. So that the phase angle is always 0 at k equals 0 and k equals n over 2. And then since the imaginary part and the phase are both 0 at the endpoints, then the magnitude at 0 is nothing more than equal to the real part at 0. The magnitude at n over 2 is again nothing more than the real part at n over 2. Now what interpretation can you apply to the real imaginary parts of the DFT? The real and imaginary parts, as shown in the notation RE of x sub k and IM of x sub k, they are the amplitudes of the cosine and sine basis functions. That is cosine 2 pi k over n and sine 2 pi k over n. And those basis functions compute k cycles in n samples, where k, as shown earlier, runs from 0, 1, 2, all the way up to n over 2. So there's n over 2 plus 1 values of those basic sine and cosine basis functions. And that is, those real DFT signals, they decompose or correlate the input signal into a series of sine and cosine functions. And you might recall that from a concept that was brought up earlier in mathematics, when you took probably your sophomore level mathematics class in college, and that is Fourier transforms. Fourier series, where you can take any continuous periodic function and you can compute it as the infinite sum of a series of sinusoids. And that's basically all a DFT is, except now it's discrete, so it has only a certain number of samples, or a certain number of sine and cosine basis functions. And recall that the input signal that we're talking about here, x sub t, is assumed to be periodic in capital N samples. As a result of this, one restriction that you'll find out that's kind of key to this, and we'll touch on a little bit at the end of this presentation, is the DFT produces sinusoids with frequencies up to what is called the Nyquist frequency. And the Nyquist frequency is defined as half sample frequency. So if you're doing a time sampling of some input sequence coming in as a function of time, then half of the rate at which you sample it is referred to as the Nyquist frequency. And the consequences of that we'll discuss again with an example at the end of this presentation referring to the Shannon Sampling Theorem. And a note about the values of real of x sub k and imaginary of x sub k in the sequence at the endpoints k equals 0 and k equals n over 2. At k equals 0, the real value of x sub n is the amplitude of a cosine function that makes 0 cycles in n samples. Well, what does 0 cycles in n samples mean? That means basically it's a constant function. So that is, the real value at k equals 0 contains the mean value of the input signal. That's very important. We'll show that with an example here, and then we'll talk again about it in part 2 when we discuss power spectral densities. That if you have an input waveform with a constant bias, you will get in the discrete Fourier transform, you'll get a value at a frequency of 0. So that's a key to you, that you have a mean value in your signal when you see a value of the discrete Fourier transform or the power spectral density at a frequency of 0. And also at k equals 0 and k equals n over 2, the imaginary part is always 0. And so the imaginary part doesn't contribute anything to the synthesis of the time domain signal. So when you want to take the discrete Fourier transform coefficients and reconstruct the original time signal, the equations you'll see never include the imaginary part at k equals 0 and n over 2. And the reason is they're always identically 0 at that point. So it may look like an oversight. Somebody forgot to include those 2 points. Well, if you included them, they have a value of 0, so it wouldn't have mattered anyway. But that's another little bit confusing factor. If you try to look at the synthesis equation, like in a textbook or something, you'll see the summation indices for the imaginary part is different than the summation indices of the real part. And that's the reason that the imaginary part is always 0 at k equals 0 and k equal n over 2. That is the ends of the discrete Fourier transform coefficients. Now, as promised, I'll show an example of a real discrete Fourier transform for a real simple sinusoid, so we can investigate what you get out and what the magnitudes of the signals would be when you compute the discrete Fourier transform of such a signal. Let's consider a 16-sample waveform consists of a 2.5 unit amplitude sine function that computes 2 cycles in its 16 samples with a constant bias of 3 units. So let's pick some numbers for this then. The amplitude then is 2.5 units. The units are unimportant here. The bias is 3 units. And the frequency f is 2 cycles in n equals 16 samples, or basically 8 samples per cycle. So then you can construct a signal like this. If you were doing MATLAB or Octave, you could type in this equation, and that would generate the sinusoid that you see plotted there on the right. And it's important to note again the characteristics of it. You see it's offset vertically by a constant bias of 3, and then it has a period of 8 samples for every cycle. So then if we were to compute the 16-point real discrete Fourier transform of x in rectangular form, it would return back an array RE, IM, and frequency, as shown in the example there. The function that's being illustrated here is called DFT underscore FFT. That's not a built-in MATLAB or Octave function. That's one of my functions that I built basically for illustration purposes, and it uses a fast Fourier transform implementation of a discrete Fourier transform. As I mentioned earlier, if you have sequences of very, very large values, or numbers of samples, it's inefficient to just do what I call the brute force summation, as shown earlier. For a real simple example, it's very easy to compute the summation and very efficient to compute that summation form directly as shown earlier on the slide. And I would encourage you to go back to that definition where of the discrete Fourier transform coefficients, and you actually put in the individual values of this sinusoid and go through the calculations, and you'll replicate what we're going to show on the next slide. But that's very insightful to do that and see what you get out. You can also use that same function, another input option that's capable of that function that I created. It will return the magnitude and phase instead of the real and imaginary, and that's the second form that you see there. Okay, there's a further example of this real DFT. Before we start the next, before we actually compute the DFT coefficients on the next slide, I'll make a couple of comments about what we ought to see. Recall that the sinusoid we're looking at here contains only one frequency. It makes 2 cycles in 16 samples, or 8 samples per cycle. It also has a constant bias of 3. So there's only 2 places in the waveform where we would expect the discrete Fourier transform coefficients to be non-zero. That would be at k equals 0, which occurs because of the constant bias that occurs at DC, or 0 frequency, and then you would expect a value at k equal 2, and that's the constant cosine component. And that's because we constructed the input sinusoid to complete 2 cycles in 16 samples. And so that has a normalized basis frequency of 1 over 8. Since 2 cycles occurs in 16 samples, 1 cycle occurs in 8 samples. So at a normalized frequency of 1/8, or 0.125, we would expect to see a value of 2. The magnitude of the DFT coefficients at k equals 0 and k equal 2 will be amplified, if you will, by these scaling factors that we discussed earlier. At k equals 0, recall again, the real discrete Fourier transform coefficient is going to be scaled by n, in this case 16. So the value of the DFT at a coefficient of 0, or an index of 0, ought to be 16 times 3, 16 times the constant bias, or it ought to be a value of 48. The magnitude at the frequency of 0.125, or 1/8 of a cycle, should be a value of n over 2 times the input value. And again, the amplitude of the input signal was 2.5 units. N over 2 in this case is 16 over 2, or 8. So then the magnitude at a normalized frequency of 1/8 or 0.125 ought to have a value of 20. As stated earlier, the imaginary part of the DFT coefficient at k equals 0 ought to be, and always is, 0. So the real value at k equals 0 will equal the magnitude at k equals 0, and that will be 48. And the imaginary part at k equals 0 will be 0. The real and imaginary parts of this DFT of this particular function at k over 2, and that's at a normalized frequency of 0.125, they're equal and opposite. So that the phase should be 45 degrees, and at 45 degrees, sine of 45 equals cosine 45, which equals the square root of 2 over 2. So then the real and imaginary part magnitudes should be equal, and they should be equal to the total magnitude times square root of 2 over 2. And that would work out to be 14.1421. So let's plot out the discrete Fourier transform coefficients that were computed by the function on the described on the previous page and see what we get. Okay, what's shown here on the left and on the right are the real and the DFT and real and imaginary part on the left, where the real coefficient is in the red line with the red X. The imaginary part is the blue line with the blue circle data points. Over on the right is the magnitude of the DFT coefficients, and I won't show the phase, just the magnitude for this particular case. Now, what we talked about before, you noticed, since I used plotting symbols, you can see where the data points have non-zero values. And if you look at the red line, again, what we expected to see was we would see values of at k equals 0, which represents the constant bias part of this simple waveform, and at k equals 1 over 8, or a normalized frequency of 1/8, because the waveform we put in completes one cycle in 8 samples. And what you see is, if you look at the figure on the left, which is the real and imaginary parts of the discrete Fourier transform coefficients, indeed, you get at k equals 0, or a normalized frequency of 0, you get the imaginary part is identically 0, as it should be. The real part is equal to 48. Again, remember that was because it should be equal to n, the number of points, which is 16, times the bias value, which is 3. So indeed, we get 48 out at x equals 0, and 0 out for the imaginary part at at k equals 0. Both of those representing normalized frequency of 0. Then the only other place where this waveform should have any output is at the frequency of 1 over 8. And sure enough, if you look on the left figure on the left, you see the red curve shows a value of 14.14, which is 20 times cosine of 45. The blue or imaginary shows a value of minus 20 times sine of 45, which is minus 14.14. As expected, and both of those data points occur at a normalized frequency of 0.125. Again, if you go to the right slide, which shows the magnitude, you can see a little bit more clearly the magnitudes we should have expected. Again, we see at DC, or at 0 frequency, we see a magnitude of 48. And that actually, if you looked at the value of the real coefficient, the first coefficient of the real discrete Fourier transform coefficients, it would have a value of 48. The only other non-zero point in the magnitude output is, again, at the the third data point, where the indices run 0, 1, 2, all the way to n over 2. So at the third data point, x2, it has a value of 20, just as we expected. And the 20 corresponds to n over 2 times the amplitude of the signal, where n is 16, so n over 2 is 8. So 8 times the amplitude of the sine wave, 2.5, would come out to be 20. And again, that occurs at a normalized frequency of 1/8 or 0.125 because the sinusoid that we chose for this example completed 1 cycle in 8 samples, or 2 cycles in 16 samples. Now we'll also discuss the complex discrete Fourier transform, but first we'll say a couple comments about the real discrete Fourier transform that we've discussed so far. There is also a thing called a complex discrete Fourier transform, which is really just a generalization of the real discrete Fourier transform. The complex discrete Fourier transform produces n coefficients of a sequence of n samples. So it produces coefficients x sub k, where the index k runs from 0 to n minus 1 of that sequence of n samples, where x sub n, the indices of the samples, run from 0 to n minus 1. Whereas recall the real DFT produces n over 2 plus 1 coefficients. Well, why the disconnect? I mean, why do we get more coefficients out of the complex? Actually, we don't, because you recall with the real discrete Fourier transform produced a real part and imaginary part. It produced n over 2 plus 1 real parts and n over 2 plus 1 imaginary parts. So then if you add those up, you say, wait a minute, we're missing 2 because we have n over 2 plus 1 real and n over 2 plus 1 imaginary. That's more than n. Well, also recall that the imaginary is by definition 0 at k equals 0 and k equals n over 2 plus 1. So in effect, the real DFT also produced n samples. They were just called real and imaginary. So, having said that, then the complex discrete Fourier transform and its inverse, or the synthesis equation, are shown by the equation at the bottom of this, or at the center of this slide. And that says basically the real DFT coefficient x sub k is the summation from n equals 0 to capital N minus 1 of the sequence of values x sub n times e to the minus j times 2 pi over n times kn, where k, the index of the coefficients of the discrete Fourier transform, run from 0 up to n minus 1. And then the synthesis equation on the right, which again just transforms back from the discrete Fourier transform coefficients to recover the original time sequence x sub n, is as shown on the right. The complex discrete Fourier transform forms the mathematical basis for Laplace transforms and for Z transforms that will be, are instrumental in control systems and other applications, which we'll touch on a little bit in part 3 of this presentation. However, for most of our signal processing tasks, the real discrete Fourier transform is adequate. And where you really get complex discrete Fourier transforms is if you have Fourier transforms of complex sequences as opposed to real sequences. And that generally doesn't come up in real-world applications where the concept of negative frequencies kind of doesn't make a lot of sense. But we'll talk on that too, especially in the discussion of power spectral density basics in part 2 of this presentation. Now again, recall that we said before, the whole concept of discrete Fourier transform requires that the input sequence be periodic. As a consequence of this requirement, the DFT must contain samples from a periodic function f of t sampled at some regular intervals. And so that introduces limitations in the analysis techniques. So the DFT can only be represented for periodic signals, or even if they're not periodic, as long as they're finite duration, you can compute the DFT. That means when you take the discrete Fourier transform coefficients, one of the characteristics of those is once you've computed those DFT coefficients, they should be able to totally reconstruct the original signal you had. That really can only be done if they're periodic signals. So if you have a sequence of some time signal of a non-periodic function, the inverse DFT cannot reproduce that entire time domain signal. It can only reproduce the portion that you analyzed. And as I said earlier, that's not really a limitation in practice, because most of the time we're just analyzing some signal that's assumed to have certain characteristics and certain frequencies that we're trying to identify. Whether it's a sensor signal we're trying to characterize, or maybe it's some sensor we want to define a filter to filter out certain frequency domains that we don't want in our control system, don't want the control system to respond to. So it's really not a limitation, but it is, in practice, you cannot reproduce the entire waveform from just a sample if it's not periodic. And that kind of makes sense. If it's not periodic, you can't make any statement about what the signal would look like after you quit sampling it. And that's kind of the premise of what we're saying here. And again, fortunately, for most of the waveforms we're interested in, they either are periodic or we're only interested in just a finite length of it. We just want to sample some discrete amount of data and make some assessment of what the data represents. Well, as mentioned earlier in the presentation, we discussed something called FFT, or Fast Fourier Transform algorithm. And what it is basically it's just a numerically efficient algorithm for computing discrete Fourier transform coefficients, or for computing the DFT. It's not another mathematical concept. That's why you won't see any discussion of FFTs here, any details at least as far as how they're implemented. So we won't get into that, but just know that there is a thing called an FFT that's just a specific implementation that efficiently computes DFTs. And as I also mentioned earlier, it can dramatically increase the speed of computing the DFTs to the order of n to the natural log of n, where n is the number of samples that you're processing or for which you're computing the DFT. And as n gets very large, which it typically is for the signals we look at, that reduction in increase in efficiency can be very significant. And most analysis packages such as MATLAB or Octave already have built-in FFT functions as well, so it's easy to make use of what they've done. In part 2 of this presentation, Power Spectral Density Basics, we'll discuss power spectral density techniques for analyzing the spectral content of the data, and we'll contrast it with the processing technique, if you want to call it, of an FFT. As I said before, the FFT is really not distinct from a PSD. You can say, well, can I get the same information that I would get from a PSD with an FFT? And the answer is yes. What PSD packages or techniques allow you to do is we'll discuss in part 2 of this presentation things like windowing, or being able to exclude certain characteristics of the signal that can kind of mask what the real content of the data is, and we'll discuss that in more detail in part 2. As a final topic of today's discussion, we'll talk to what's called the Shannon Sampling Theorem and data aliasing that can occur if the signal being investigated is not sampled at a high enough rate. To paraphrase what the Shannon Sampling Theorem says is, if a continuous signal is sampled at a frequency at least twice the frequency of the signal's highest frequency content, then those digitized samples can be used to completely reconstruct the original continuous signal. Or, said another way, if the signal being sampled contains no frequencies above the Nyquist frequency, which is defined as half the frequency that you're sampling it at, the frequency content is preserved. So you can use an inverse TFT to completely reconstruct the original continuous signal. However, if the signal being sampled does contain frequencies above the Nyquist frequency, the frequency content of the signal above that Nyquist frequency will be aliased, meaning it will be wrapped down to lower frequencies, and it will be as if a phantom signal at a different frequency has appeared. And that signal at that, what I'm calling this fictitious or phantom frequency, will combine with any real signal that happens to be there. So then that will really mess up the calculations, and you'll get an erroneous answer. And usually sample data systems use things called anti-aliasing or low-pass filters that are designed to attenuate any signal above the Nyquist frequency so that anti-aliasing cannot occur. In other words, you'll define for a given sample frequency in your, say, discrete controller, you'll actually apply a low-pass filter that will cut off any frequency content above the Nyquist frequency, so anti-aliasing cannot occur because those higher frequency signals will not appear in the filtered signal you're actually processing. Okay, let's start with an example. We'll do several examples where we build a waveform with a 10 Hertz frequency content, which means if we want to sample that correctly, we need to sample it at least 20 Hertz. In other words, twice the frequency content of the highest, or twice the frequency of the highest frequency content in the signal that we're analyzing. So in this case, the example is going to be a 10 hertz frequency. So we must sample at least 20 hertz to be able to get a correct discrete Fourier transform of the signal, which would allow us to completely reconstruct the time domain signal from the samples, or from the discrete Fourier transform signal. So just as an example, for this case, we'll sample it at 30 hertz, 22 hertz, both of which should be okay since they're greater than twice the highest frequency in the signal. We'll also sample it at 18 and 12 hertz, which should not, or is not fast enough and should cause some of the aliasing problems that we're discussing or describing. And we'll see what happens when we do each of those. So at the first case we'll take that signal and sample it at 30 hertz. So then the sample frequency, the frequency in the content of the data is 10 hertz. The sample frequency in this case is 30 hertz. So the normalized frequency, or frequency divided by sample frequency, is 0.33, which is less than 0.5. And again, the reason 0.5 shows up is, the discrete Fourier transform will produce frequencies in the range of normalized frequencies from 0 to 0.5, or 0 to half the sample frequency. So any frequency content that has a normalized frequency 0 to 0.5 would work okay. In this case, it's 0.33, so we should be able to correctly get the signal we are expecting. So again, we take this 10 hertz frequency, 10 hertz sinusoid. We compute PSD of it, which again we'll discuss in part 2, how to compute PSDs and what they mean. But as an example, what you'll see here is now when we compute the PSD of that signal, we see a nice clean spike at 10 hertz, which is what we were expecting since the waveform had 10 hertz in it. And just for further interest, you can actually compute the area under that PSD curve since it is a power spectral density. The integral of a PSD then gives you the RMS value squared. So if you actually compute a kind of simple integration of that signal, assuming it's a triangle wave, you get an RMS value of 0.5, and that's what it ought to be for that input sinusoid, which should be 1 over square root of 2. So, RMS ought to be 1 over square root of 2. So sampling this 10 hertz signal at 30 hertz was correct, and we got the output we were expecting at the frequency we were expecting. Now let's look at it, sample it at 22 hertz, again, which should be sufficient because it's greater than twice the frequency of the input signal. So again, we do the same thing there, and again we see now a nice little spike in the PSD at the lower right, centered on 10 hertz, just like it should. And again, if we compute the area on the curve, we get an RMS of 1 over square root of 2, like we would expect. Now let's sample it at 18 hertz, which is less than twice the input frequency, and we should start seeing some aliasing occurring. Now what you'll see is when we calculate the PSD of this samples where we sampled it at 18 hertz, now we get the blue line that shifted over from the red line, which is the correct PSD. Now you'll notice it showed up at 8 hertz. Well, why 8 hertz? That's because at 18 hertz, the 10 hertz input frequency content divided by 18 results in 0.555, which is greater than 0.5. And recall again, the discrete Fourier transform returns signals from 0 to 0.5. So the 0.555 actually going to wrap back around to 1 minus 0.555. So that results in, if you take 18 hertz times the quantity 1 minus 0.555, you get 8 hertz. So that signal has now shown up as an 8 hertz signal when it was really a 10 hertz signal. So it's aliased down 2 hertz. Now let's do the same thing and look at it at, I believe the next one is 12 hertz. Now we're going to take that same 10 hertz signal and analyze it at 12 hertz. And what you'll see here at 12 hertz, the normalized frequency is 10 divided by 12, or 0.8333. Now that wraps around to a normalized frequency of 1 minus 0.833, or 1.833 times 12 results in 2 hertz. So now even though the input signal had frequency content at 10 hertz, it showed up as 2 hertz because we undersampled it significantly. So summarizing, what you saw is when we sampled this 10 hertz frequency content at 30 hertz, we got a nice spike at 10, like you see here in the red line on the lower right PSD. When we sampled it at 22 hertz, it still showed up as 10 hertz like we expected, When we sampled at 18 hertz, now it started showing a content at 8 hertz, which is incorrect. And now when we sampled in this example at 12 hertz, it showed up all the way down at 2 hertz. So what the ramification of this would be is if you sampled this signal at 12 hertz and you actually had a signal at 2 hertz, the content that's truly there at 2 hertz would be combined with the power of this signal that's really at 10 hertz, and you get an incorrect output in your results. You think you had a more signal content at 2 hertz than you really have. So that illustrates the importance of sampling at the proper frequency. So therefore, again, just summarizing this whole section, when you're sampling signals, you must sample it at least twice the frequency of the highest frequency content in your signal. And therein lies the problem. A lot of times you don't know what the maximum frequency is. If you're trying to sample an unknown signal, you don't know exactly what's in there. So that's why if you're going to use this signal in some application, you better make sure you run it through an anti-aliasing filter that's at least twice as high as your sample frequency, so that you by definition will not allow any signals beyond the sample frequency, or beyond twice the sample frequency. Well, this concludes part 1 of this 4-part series for Introduction to Digital Signal Processing. In this part 1 mathematical concept, we've covered the following. We defined the definitions of Fourier transforms and discrete Fourier transforms and mathematical prerequisites that we're going to need, and the analysis techniques that we'll need for the other 3 parts of this presentation. We talked about Fourier transforms and convolution, discrete Fourier transforms, fast Fourier transforms, which again is just a more efficient way of computing DFTs, and we discussed the Shannon Sampling Theorem and data aliasing. In part 2, power spectral density basics, we'll cover the following, primarily how to use PSD functions that you might find in packages like MATLAB and Octave, and a demonstration of a signal that contains several frequencies, and we'll run it through a PSD function and show how to analyze and interpret the results. In part 3, entitled Implementing Discrete Filters, we'll actually see how we implement these DFT concept, discrete Fourier transform concepts, and convert from filters from the Laplace domain to the continuous Z-domain filters using Tustin's rule or bilinear transformations. We'll also show how to implement recursive filters to implement these discrete filters. Finally, in the last and final part 4, entitled Typical GNC Applications, we will cover the following: normalized frequencies, methods we can use to verify a transfer function if you're given discrete filter coefficients, an example of how to use a discrete filter to implement a low-pass notch filter to actually condition a signal that has higher frequency content. Well, again, this concludes the first of 4 parts. I hope you have found this discussion, this presentation, to be useful and informative, and I invite you to continue with parts 2 and 4 of my presentation. Thank you.